Hello, this is Dan Alford with ARC Specialties. This is another in our series on designing for automation. People are worried about robots taking their jobs, but I can assure you if robotics was easy, my life would be easy, and it's not. So for the last 40 years, I've done nothing but automate industrial processes, and through all these years, we frequently will make suggestions to customers on how to facilitate automation, either to make it easier or to improve their acceptance rate or to improve the quality of the part. And we're going to talk about the lessons we've learned when customers listen to us and when they don't. So today's example is sand screens. So this is a sand screen that goes in an oil well to filter the sand from a gravel pack so that the oil will flow through the gravel pack, through the screen, and up to the surface and to the refinery. So the way these are made traditionally was on an old lathe. And so we have these rib wires that go full length on the part. And these are 40 foot long in the real world. This is just a small section of it. And then we spin these rib wires, as these are called, and then we wrap the wrap wire around it. These are not round wires, they're trapezoidal shape. But the gap between the wires is what controls the filtration. And this is a very critical tolerance here. People want to hold this plus or minus 1/1000th of an inch. So that's a third of a human hair. That's hard to do, particularly when you understand that the quality on the tolerances on the wire will float by that much. So the width of the wire will change as much as your total part tolerance is. So in other words, you can't get there from here because the variation in the width will exceed your tolerance of your gap, unless you measure that width in real time as it's flowing in. So we're spinning this part at 100 RPM. We're welding the wrap wire to the rib wire at 100 welds per second, which is a challenge in itself. But the most challenging part about making weld screens is holding that gap, plus or minus 1/1000th on 99% of these gaps. So traditionally, this had been done on an old machine tool lathe. In a machine tool lathe, the headstock and the carriage are mechanically coupled together. And this is usually a function for threading and such. And so that means you get a very specific pitch, which is what you want when you're threading bolts and such. But in this case, we didn't want that. We wanted to be able to change that pitch. And that's what we had to convince industry of. We can achieve plus or minus 1/1000th gap over 99% if they will allow us to change the pitch. So we're measuring the width of this wire in real time as it flows into the machine. And if we notice it trending thicker, all we do is increase the pitch, the helix. And that way we maintain the gap in real time. And initially there was some pushback on this, but in reality, nobody really cares what the pitch is. And once we were able to control that variable, then we were able to control the variable which they really cared about, which is gap. So we're welding at high speeds, we're welding without sparks, and we're holding plus or minus 1/1000th on the gap because they're allowing us to change the pitch. But what that means is you can no longer use a mechanically coupled headstock and carriage. You're now electronically coupled. But modern controls allow this. And the proof's in the pudding. We've got these machines running all over the world, I think in 6 different countries now, making good parts out of bad wire all over the world. So, great example of where we had to change the design of the part. We had to change it from fixed pitch to variable pitch in order to maintain gap. I hope this has been a benefit to you. I hope you find applications in your world where you can improve your part for automation like we have on this one. And I look forward to seeing you again soon.